Let's look at our stadium wave function and interpret a function value and take two derivatives and interpret each of the derivative values. Just a reminder that z is the height of the head of the person who's sitting in seat X t seconds after the wave began. Here's the formula. The point I want to pick, I think, is just the 0.62. So let's plug that in first. What I want is I'm just going to take f of 6,2. That's supposed to be something like 5 plus cosine. That's going to be 3 minus 2. So this is going to be equal to 5 plus cosine 1. My calculator says this is about 5.540. I'm underlining that because that's as far over as I did it. Remember, the units here are feet. And what this means is the person in seat 6, the head of the person in seat 6, is 5.54 feet high. Two seconds after the wave began. Now remember, this is a long interpretation, and the derivatives are going to be even longer. So just recapping, we plugged in 6,2. We got 5.54 feet, and that means the head of the person in seat 6 is 5.540, approximately feet high, 2 seconds after the wave began. Now this section is about derivatives, not about function values, so let's take a derivative, get a function value, and see what we can do with it. Okay, I'm going to take the derivative with respect to x first. So what I want is I want to take the derivative with respect to x, and then I want to plug in 6,2. So if I take the derivative with respect to x, the 5 goes away. I get minus sine. This is cosine of blob, so I got 0.5x minus t like that. The blob is linear in x, right? The derivative of t is going to be 0 when we take the derivative with respect to x. So we're just going to get 0.5. Now I don't want to say that the derivative at that point is equal to that whole derivative, so we use an evaluation bar that looks like this. Like that. And so what I should get is something like minus sine. I think this is going to be of 1 times 0.5 at 6,2. And when we plug in 6,2, I think we get something like minus 0.421. Now, what are the units going to be? Just a reminder, when x is the variable, all I know is that this thing is wiggling, yes? Is that z goes up here, x goes down here. The other notation looks like dz dx. We read it partial z, partial x, but there where you can see the units, right? It's going to be feet per seat. Feet per seat. Feet per seat. Now let's get rid of my little graph here and try to interpret this. What does this mean? Right? Badly, if seat goes up by 1, feet goes down by minus 0.421, right? Now, how can seat go up by 1? If I'm looking at seat 7 and at time equals 2, right? Let's see here. How about this? The head of the person in seat 7 is about, remember this is a derivatives, it's not exactly linear, 0.421 feet lower than the person head in seat 6. Not always, 2 seconds after the wave began. Woof, right? So you can see taking the derivative isn't the hard part. The hard part is actually trying to figure out everything that went on. So we plugged in a number and we interpreted it as a height of heads person after t seconds. We took a derivative, and this actually told us about how much different in height the person in seat 7's head was than the person in seat 6. All right, let's take the other derivative and interpret that. Now the other derivative should be with respect to t. So let's do that. I want f of t. I'm sorry, this is ft of 6, 2. So I want to take the partial derivative with respect to t. The 5 is a constant, it goes away regardless. So I'm going to get minus sine of 0.5 x minus t. Remember, we just took the derivative of cosine of blob. Now I multiply the derivative of blob. But the x is now a constant, so the only thing I get here is minus 1. I don't want to say that the slope at that one point is equal to this whole function, so I put an evaluation bar in like this. And I plug it in. I'm going to get minus sine. This should be 1 times minus 1. That should be the sine, roughly, of 1. And I think that's about 0.841. Now before we interpret it, let's do what we did before. Here we're holding x constant, and so when we take a chop, t is going to go over here, z is going to go up like that. We're going to get partial, remember it's doing wiggling, yes. The partial of z with respect to t is a derivative we just took, but now we can see the units, right? This is going to be feet per second. Feet per second. Now, if we just would interpret it, we would say the person's head is going down at 0.841 feet per second at that moment. That's not actually the way it gets used. These things actually get used to try to predict something else. And what I want is I want to say, okay, if seconds goes up by 1, the person's head should go up about 0.841. Well, how can the seconds go up by 1? By going from 2 to 3. So what we're going to say is, the head of the person in seat 6 goes up about 0.841 feet during the 3rd second. How's that? During the 3rd second. I think that's right. Of the wave. There's a nice interpretation. You can see the interpretations are long and slow, but this is actually, if you're not a math major, this is what actually makes it valuable. And this is what they expect us to be able to do to explain the derivatives to people who hate math. All right, moving on.